You have to start it, otherwise people will not see anything.
Okay, good afternoon and welcome to the last afternoon of the last day of CODS-COMAD. It's been a very exciting conference, and I hope you all got engaged with a lot of different activities. On behalf of Pushpak and myself, we would like to thank everybody who's been involved in the organization of this conference. As you probably all know, a conference like this really takes a lot of effort, collective effort, and every person plays a critical role. So of course, there are the PC chairs. There was the research track, Praneeth and Luaika, and there is the applied data science track, which has Tanuja and PK. So we'd like to thank them a lot for everything you have done. I guess PK takes the credit for everybody. As I mentioned, there are lots of other tracks, obviously, and lots of other things. So there are the tutorial chairs, Animesh and Kalpriya. Thank you. There are the demos chairs, Mayank and Anoop. If you are here, just wave your hand or something. Then there was the Young Research Symposium chairs, Prithi and Bivas. Of course, we had very influential diversity and inclusion chairs. They were very active throughout. Ravi and Chitra, thank you. And please don't forget, there is going to be a panel, diversity and inclusion, after the last keynote. So stay for it. It's going to be very good. There are the proceedings chairs, Abhinadan and Sharu. Publicity chairs, Rajiv and Arunesh. Finance chairs, Shekhar and Raj. And where's Raj? Okay, Raj deserves a special applause. Really, without Raj, I don't know what I would have done. I wouldn't have arrived at IIT Bombay, probably. Sponsors chairs, Shurya and Yogesh. Local arrangements chairs, Biplap and Manoj. Web chairs, Abhishek and Swaroop. Virtual event chair, and really Atul, without Atul's constant working all the time. He's been here for every session. The Student Travel Grants Chair, Koyel. And last but not least, all the steering committee, and especially Sudarshan, who really helped us with a lot of the details and the ongoing work. So,
to call the organizing committee. Chair,
Biplap, so please.
Hello. Yeah, very good afternoon. So apart from the steering committee, there are a number of people that we are very grateful in organizing and executing the conference. So the event management team led by Neetu, they did an extremely good job in setting up the booth, doing all the other VR and AR related thing in time. So thanks to them. Then the PHO, the Public Health Office, ensured that everything are clean and hygienic and everything are in place. Then the VMCC committee and the staffs here, they ensured to run the conference smoothly for all the 4 days. The IDC for providing the standees for the poster. And for the catering and the decoration, we have a very dedicated team led by Sheikh, so who did the food and all the other things. Now coming to the local organizing team, for I have a list of volunteers who are the masters or the PhD students: Sachin, Mikhil, Shravani, Vineet, Harsh, Hitul, Prashil, Prathamesh, Durgesh, Ankit, Swarnendu, Shabnam, Shivam, Sai, Swarup, and Vineet. And last but not the least, Dhirendra. He actually worked extremely hard just to ensure that the conference runs smoothly. He was traveling all through, and very thanks to Dhirendra. He's here. Yeah, thank you. Yeah, so the volunteers who are here, you can please come up to the stage. Yeah, or stand up. Yeah, yeah, just. Thank you. Thank you.
Yeah, it's here. And now we have the next keynote. Yeah, Sriram, who's presenting?
Yeah, Sudarshan is there.
Sudarshan, okay.
And of course, the biggest thanks to the two people who made all of this happen, Pushpak and Amr. Thank you so much. So it gives me great pleasure to go to the next part of the session, which is to introduce Sriram Rajamani. Sriram, as many of you may know, is heading the Microsoft research team in Bangalore. And he has a very illustrious career. He was at Guindy Engineering College and later Berkeley. And he has had a very long stint at Microsoft in research. But his biggest claim to fame, for all you old-timers here who remember the blue screen of death. How many of you remember the blue screen of death? Oh, a lot of people do. More than Sriram would be happy with. So Microsoft was notorious for the blue screen of death, and it was hurting the company's reputation. And in came Sriram to save the company, which he did. It turns out that the fault was not Microsoft's code, but the device drivers and so on with other people installed. So what to do about it? So Sriram brought in program verification to make sure that the device drivers were bug-free and would not crash Windows. And after that, there was a steep jump in the quality of Windows. I have not seen the blue screen of death in many, many years. So it was a tremendous success, and it has been very widely recognized, both at Microsoft and outside. He has won the, which conference was that? CAV Test of Time Award. He's also an ACM fellow. And after that success, and this is also very interesting because programming and verification were kind of two different things. It was viewed as more theoretical, but Sriram is one of the people who made it practical. So after verifying programs, he's now moving to building the programs directly and removing all these programmers who introduced bugs in the first place, getting them out of the way and doing it correct by construction, which he will talk about today. Thank you, Sriram.
Yeah, thank you for that kind introduction, Sudarshan. So I'll talk about AI assisted programming. And actually, in some sense, actually, when Sudarshan was, and correctness actually will play a major role in this talk as well. And I sometimes think actually I spent some time in my life verifying code that was written by humans. Now I spend time verifying code written by machines. And they're quite different, by the way, and maybe we can touch on that as we go through this talk also. And this is talk done with many, many wonderful collaborators, as well as research fellows and interns over the years. I'll start with this slide where I sort of contrast between what I sort of think about as programming and learning. And the one on the left, I sort of think about it as a manual way to go from a specification to a program that satisfies that specification. A typical example of that I would think about is something like sorting a sequence of numbers in ascending order, and then you coming with an approach and writing code to satisfy that intent, and contrasting that with learning, where the framing itself is different. It is not just a different approach or a different technique. That a very fundamental part of what I think about as learning is the fact that your specifications are either imprecise or incomplete or both, in the sense that you may have a set of pictures that you want to classify and you may have some training data with examples and labels. Or, you may have, if you're using, Copilot and so on, maybe a partial textual representation of a function. And then these learning techniques, either from examples, come up, learn a function or learn a model that generalizes and works as long as the test distribution is similar to the training distribution, or with whatever context you may give a large language model, however ambiguous it may be. These models can look at all of the other code that is present in the world and complete them with that ambiguous intent in mind. So I contrast between these two. And I've been working in this area for the past few years, but the past year or so has been rather disruptive in this space, as you may know. And the disruption in the past few years is all because of the perfect storm that was created by the transformer architecture, self-supervised learning, and compute power. So in here I have, actually, unfortunately, I'm sorry, the fine print is rather small here, but what I wanted to show was that this is Elmo. Elmo started with, I think, 94 million parameters. Somewhere here is actually Megatron, which is 8.3 billion. This is GPT with GPT-3 with 175 billion. And here is Palm with 540 billion parameters. And you can sort of rapidly see how this is sort of going year on year. And this, a colleague of mine showed me this, which I found very interesting, which I want to show it to you. Here is actually a description, a portrait photo of a kangaroo wearing an orange hoodie and blue sunglasses, standing on the grass in front of a Sydney Opera House, holding a sign in the chest saying, "Welcome, friends," right? And what he did was actually he sort of asked a 350 million parameter to draw this, and then so on and so on. And actually, just look at this one. This one captures that intent so well, right? And I got this information from some of my machine learning friends that the 8 billion parameter models were starting to do question answering, arithmetic language understanding. And once we got to 62 billion, these models started doing summarization, translation, and so on. And once you got to 540 billion, we could do code completion. And people call these as emergent behaviors. And this last slide, I actually calculated myself. I calculated myself as actually, if I were not working for a company, and if I have to get GPU resources, I just did an arithmetic based on number of parameters and how much compute time I would roughly need. I just did some back of the envelope calculations. And this is how much it actually cost to actually train these things, right? So this is how much this field is changing because of scale, right? But of course, actually, in this talk, I'm not going to talk about all of this image generation and so on. I'm just going to talk about coding. But I will talk not just about large language models. The first part of the talk will be about large language models. Then I will actually talk about other smaller models as well. But I've been quite influenced by Copilot, which, if you have used, it's an extremely interesting user experience where you could actually go inside your Visual Studio editor. You could actually write the beginning of a function. You could write some comments. And then, as you type, it completes. And this completion, right? I've been coding with Visual Studio for a while. In the past, what you would get is actually when you type response and you type dot, it will actually complete, what follows. That has been going on for a while, right? But this one actually completes entire methods, completes entire lines, and it's more often than not, it actually does an extremely good job, right? Which is stunning, and this is causing lots of people are paying attention to it. Just in the last month, I saw 2 articles. This was in the Viewpoint in CACM. The title is very interesting. It says "The End of Programming." And this one by Bertrand Meyer is a little bit more balanced. It actually says that he's also stunned by how much automatic program generation is doing. But then he says, "Oh, there are all these issues." So this is actually one view of how much disruption this is causing. This is a counter view, which is these people in NYU. What they managed to do was there is actually something called MITRE, the MITRE Corporation. The MITRE Corporation keeps a list of top 25 vulnerabilities, and actually they update it year on year. And this is a very empirical measure, right? So what they do is actually every year they do statistics on all the security vulnerabilities that were exploited and caused trouble in the world. And they score them based on how many times that security vulnerability, that class of security vulnerability created trouble. And they take the top 25 ones. And what these researchers did was that by appropriately prompting, they were able to get these large language models to generate every one of these top 25 vulnerabilities. They were able to get these models to generate vulnerable code in that category. And out of this many programs, 40% of them, they got these models to generate this vulnerable code. And it's not like these vulnerabilities are hard to detect, because there are tools like CodeQL, verification tools, much like the ones that I built. So you can actually run them, and they will actually flag these as vulnerabilities as well, right? And so my view in this talk is actually, I'm neither going to be exuberant like these guys in the previous slide. I'm actually not going to be a downer like these guys also. I'm going to be somewhere in the middle, in between the two. So I actually think that these kinds of machine learning techniques generate code is incredibly impressive. But I think all of these things, like, can they produce vulnerabilities? Can they produce robust code? I think those can be improved. They can be improved, and they can be improved by combining programming language techniques with the machine learning techniques. So that's going to be the gist of my talk. I think, by combining these kind of machine learning models with program analysis techniques, you can improve robustness, you can improve interpretability, you can improve performance. And I'm just going to give you case studies to sort of recall our experiences along these over the past few years. So that's going to be the nature of my talk. And without any further ado, I'll just jump right into the first experience, which uses programming language techniques to improve the quality of code generated by large language models. So there's a project called Jigsaw that we've been working for a couple of years now, where what we do is that we take these large language models. So Codex is a large language model that is behind Copilot, and GPT-3 is sort of the same class, but Codex is actually trained more with code from open source repositories, GitHub repositories as well. And actually, it actually uses GPT-3 as a base model, and then it's trained on a lot of code. That's how Codex was built. But it's the same class, same number of parameters, roughly. And so this is a large language model. So we sort of add guardrails around this large language model by do some pre-processing on the input, and most importantly, we take the output that is produced by this Codex and then do analysis on them. We use analysis, synthesis, we do testing, and so on, and improve its quality. And we also learn from user feedback and improve the post-processing itself. Though actually, I think it's also possible to take the user feedback and improve the model itself, which is actually these days, they call it as, after ChatGPT-3, ChatGPT, you hear about this RLHF that is actually happening, which actually takes user feedback and improves the model itself. But I'll talk about taking user feedback and improve the post-processing as well, right? So the one thing that I will add to the framing of the problem is that in Jigsaw, we not only take natural language, we also take an additional, what we call as multimodal specification. We also take input-output examples. And the reason why we do that is because to use program analysis and so on, you need actually some precise specification of your intent, right? And the natural language itself typically doesn't provide the level of precision that you need. And an extra specification with input-output examples, even though it may be incomplete, is still nevertheless useful if you want to use program analysis techniques, synthesis techniques to actually improve the quality of what this produces. And the first instantiation of Jigsaw we did was for pandas. You may have used the Python pandas package. It's actually very widely used. And you could sort of think about it as use it for data manipulation. It's a programming model in which you have essentially tables, and you can write Python code to do transformation at the level of rows, columns. You could do joins. You could merge columns and merge tables and so on. And so what we do is actually, if you want to use this with Codex, you could start with the natural language and it produced pandas code, which is hopefully correct. But in Jigsaw, what we do is that we, in addition to the natural language, we also ask for test input-output examples, which you sort of give it as, with this data frame as input, you can produce that data frame as output. Most people actually just give one example. And then what we do is actually we take the code that is produced and use this as some kind of touchstone, right? Even though it's incomplete. you can actually just run the input on the produced pandas code and actually check whether it is consistent with the output that you desire. And if it is not the case, you can actually start with this code and start transforming it using formal methods. There's perturbation. You could sort of think about it even as model checking, where actually you are exploring the space of transformations that you can actually apply on the input, and then see whether you could make it satisfy the output. And but even then, right, there's no guarantee, because this these examples may be incomplete. You may be giving only a small number of examples, and it might fail on different ones, but which typically doesn't happen with pandas, because in my experience, right, if you give a reasonable data frame and say that this is the output you expect, typically it covers all cases that you want. So this is how Jigsaw works. Here, I'll explain this in an example. So here could be a natural language query. Remove a substring name from column C of data frame df, and we could run it through an LLM, and the LLM produces this. But if you just see this, right, there is a word substring here, which this code seems to have ignored. And here is actually an actual input of the example, where the intent is that these two rows have a substring name inside them. And the intent is actually not to remove the row. The intent is to remove just the substring from the field value of those rows. But if I give, if I run this code on this, I mean, there is no column has the exact string name %. So actually you will get the output as the exact input you will get as output, because this is name : something, and the remove is actually only for the exact match name : whereas actually if you run it with Jigsaw will actually produce the correct code that you want to actually, you want to replace name : with a blank, which is actually what you want. And if you run this code and this input, you will get this output. What might happen with Jigsaw as well is that Jigsaw is an incomplete system, so it might not be able to discover this, and it might actually just give the incorrect code to the user. But Jigsaw also observes what the user does with that code. In the sense that suppose the user edits this code to this version, then Jigsaw will actually learn that for this input, you have to do this, and it will actually use that. And next time you call it, or even call something similar to that, it will actually apply that. So that's essentially how Jigsaw works. So some more details on this. What Jigsaw does is that it actually takes code that is generated by models, and it does a careful set of mutations with it. Because one of the things that we saw was that the generated code sometimes has variables just present in the wrong places. So it takes variables and it just permutes them, and it can actually change df2.merge to df1 to df1.merge to df2. And one of the things we built was a sandbox where we can actually run this code on this input. When you do sandboxing, you have to be very careful to make sure that malicious code doesn't actually just delete all the files in your disk. So that's why you need to run a sandbox, because if you're running a language model, you have to be prepared that it might generate anything. Our users, in order to trick this, might actually do delete your file system and so on. So basically, that's why actually in order to do this, if you want to run the code to actually check whether it works, you need to be careful to run a sandbox which we built, and then systematically search over various kinds of transformations. And then for each one of them, we have this touchstone. We can actually run them to check whether the input, if you started the input, you produce the actual output. The other thing we do is, like here, for example, this is the code that is produced by the LLM. And because we understand, when Jigsaw understands that the type structure of what the API actually needs, it knows that there are some default parameters. It knows the number of parameters. It knows the types of them. So it actually enumerates over them. And here it manages to find that if you have add keep equal to false, then actually for the input, it actually produces the correct output. So it can do that. And this is an interesting example where this code doesn't even compile, because it has mismatched parentheses, and then the user edits it and introduce the current parenthesization, and Jigsaw learns a transformation that actually takes incorrectly parenthesized code to correctly parenthesized code. It actually is able to learn this kinds of transformation. And so the first two techniques are more search-based, where you sort of take the output that is produced and sort of search variants of it to see which ones satisfy the input. And the last one is sort of more data-based, where you sort of let users use it, profile what the users do, collect data from it, and then learn and transformations from it. So even though we did this with testing, I can imagine building a version of Jigsaw with verification, where instead of test cases, if somebody gives me preconditions, postconditions, and so on, we can replace the testing part of Jigsaw with the verification condition generator, much like the ones that I've built in the past. But people use this for things like pandas and so on. So I imagine that in some sense, what we're doing here is actually we are improving the correctness by an extra notch by using testing. You could actually increase the correctness even further by writing a formal specification and using a verifier. But the amount of effort doing that will be very large. And this community is nowhere near that right now. So that's why we are doing this. But conceptually, you can actually push that to include formal verification in addition to testing as well. This slide is about how we actually learn the transformations. I'll skip this one because there's a lot of detail. So let me tell you actually how we evaluated the system. We evaluated the system by running 2 hackathons in our lab. And in each hackathon, a bunch of participants they volunteered. They actually, Sunita knows these are all RFs in our lab. So we said that everyone would get like an Amazon or a Starbucks coupon or something like that. Then that's enough for them to all register and try. So what we gave them was a pictorial description saying actually, for this example, you need to produce that. That's the only specification we give the students. And their task is to generate pandas code to achieve this transformation. That is the task you give. And you get points depending on how many tasks you manage to get right within a certain amount of time. You get like 1 hour or 1.5 hours or something like that, and then you have to do that. And then we log all the interactions they have. And there is a test group and a control group. The test group is given access to Jigsaw. The control group has only Codex, right? So that's the two. And so for this problem, right? Here could be one user who says replace France. Actually, I'm really sorry. Actually, I think there's something wrong with this projector. So replace France with FR in the country, and Paris with PAR in the city column. So actually, this is France, and this is FR, and I think this is Paris, and this is PAR, and so on. So it turns out that actually if you give this natural language input, Jigsaw produces the correct code. But this was some other user did not give this prompt. I mean, they gave some other prompt in natural language, and Jigsaw produced an incorrect prompt. And typically what people do is that they go there and replace this one natural language question with a different one to see whether they get the right one, or they edit the code output, and we can sort of monitor what they actually do, and we record all of that. And then we did something very interesting, which is one of the things we did. The reason why we did 2 sessions was we wanted to understand whether the rules that we learned, they generalize across data sets. So these 2 hackathon data sets, they were not identical. They were different programs, but they used the same kind of constructs of pandas, like join or merge. The solutions, you had to use the same kind of primitives, but the problems are very different, right? So this was actually with GPT-3 and Codex, what fraction of the queries, the model returned correctly, and what fraction of the queries, Jigsaw returned correctly. And you can sort of see, the one thing we did was actually this hackathon 2, we sort of gave harder questions, right? And what we noticed was actually that both models, both GPT-3 Codex as well as Jigsaw performed worse in the second one than the first one. But what we did was actually, if you take the feedback, we actually ran Jigsaw first on this one, and we learned all the rules, and then Jigsaw with feedback actually performs much better. And this is consistent with users Jigsaw in the sense that it learns from simpler examples, and the rules translate and generalize to more complicated examples as well. And if you want to learn more about this, you can read our paper in ICSI last year, where we give a detailed account of actually how the system works. Currently, what we are doing is that we are using a similar approach to identify security vulnerabilities in JavaScript. Can I get a quick show of hands, actually? How many of you write JavaScript code here? Some 4 or 5 people. So maybe I think I have to explain what the security vulnerabilities in JavaScript are and how they look like. So here's some JavaScript code. And this was generated by Copilot, where you write only the comment, call action with payload, and then Copilot generates this code. It turns out that this code is vulnerable. Actually, I must first maybe give some basics on how vulnerabilities can arise in programming languages in general and in JavaScript in particular. See, most vulnerabilities arise because of this facility called eval in programming languages. What eval does is that eval allows at runtime the construction of code from data. Right? So I can actually, the user can actually type some, you can go to a website, the website maybe gives you user ID and password. But nothing prevents the user from writing a program in the user ID field, because it's just a string. I could just write a program, and you can sort of trick the way the program is constructed into taking that code that the user writes and having the system execute that code, right? And then you can sort of take over the machine, you can delete some files, you can actually look at something that you're not supposed to look at, right? You could do all of those kinds of things. Maybe you could transfer money to your account. That's another thing you could do. And by the way, these do happen. People lose money because of these kinds of things. And all of this happens because you are tricking the system to execute code that it was not intended to execute. And this one seems extremely innocuous, that what we are doing is that we are actually looking into a table of actions and taking an action, and then actually you are executing this action. That code is not there, and then you are executing the action somewhere. And but it turns out that if you know JavaScript has something called dynamic inheritance in the sense that what you could do is that actually you can have a user can at runtime add properties to an object. And when you add properties to an object, you can override a base method, and the user can actually have, when you call this action, it's actually the user's code that could actually run. It could happen, and if you're a safe JavaScript programmer, the way you would prevent this problem is that before you execute the action, you actually check whether this action has its own property, and that means that it has not been overridden against the intent of the programmer. So this actually is the way to write safe JavaScript code. And if you don't do that, your code might work, but it can be hacked. In the sense somebody else can now run their own program, and not the program that you intended when this happens. So in general, this problem is called an information flow vulnerability problem. And there are many such problems that you may have heard about, something called cross-site scripting. This particular thing is called unvalidated dynamic call. Cross-site scripting is something similar. So there's a lot of database people in the audience. SQL injection is also very similar, right? When you're trying to construct a SQL code using a bunch of strings, and one of the strings is actually injected by the user, right? And what you think is actually the user is injecting maybe the field name or something like that, but instead of that, they're actually injecting a whole code. Maybe they want to steal your password or something like that. So they could do that. So all of these, right, they're quite non-local. Like here, for example, here's a function, and this function, picks up, this data, and it picks up this field and runs this, and then in here, whatever is passed into run, it's picked up and actually is run, and then here actually this, his own property has not been checked, right? But there's a flow of data here, and you have to put this check somewhere in there, right? Otherwise, this code is vulnerable. So how do you solve this problem? So the way people do this is that they learn patterns based on vulnerable fixed pairs of programs, right? And a lot of existing approaches use version control. So what they do is actually they look at, now there's lots of repositories that are available on the web. They go look at comments to figure out, unvalidated dynamic call. What are the instances of unvalidated dynamic call that have actually been found in code bases? And they look at check-ins and mine patterns where they have fixed it. And then using those vulnerable fixed pairs, they actually learn rules and then apply those rules on similar looking code to automatically fix those vulnerabilities. One of the difficulties about doing this is that version control logs are very difficult to mine. Right? If you ever tried that, right? Because they have so many other changes. And furthermore, what actually happens is that people seldom do only one change. Along with that, they'll do other changes also. So you will not know which one of those things fix the bug, which one of those other things do, right? So one of the things we do here is, for these kinds of vulnerabilities, we have a different approach to generate these kind of training data, which involves taking a good code and perturbing it to generate bad code. So let me just explain how that works. So all of these kinds of information flow vulnerabilities, safety, they have this thing that user can input, and the information flow people call this as a source, untrusted source, the source of information. And this information sort of flows through a data flow path into what we call as a sink. And the sink could be an execution of a function, an execution of a database, somewhere where you're executing code, right? And the correct way to defend against information flow vulnerability is that you have to actually sanitize the input and make sure that it actually doesn't have code. It's only data, it doesn't have code. That's basically what you have to do. And so what we do is that we use a static analysis tool to, usually static analysis tools detect only vulnerabilities, but you can also rig a static analysis tool to look at code that is written correctly, but identify, here are the source, sanitizer, and sink. You can actually have a static analyzer do that, because what a static analyzer does is that it actually checks that on all paths anyway. And then if it finds a path in which that sanitization is not available, then it actually flags it as a vulnerability. But even for correct code, actually it is going to do that work anyway, right? So what we do is actually we use that information and then introduce the bug by deleting the sanitizer, right? And by doing this, what we can do is that CodeQL is now a widely used static analysis system, in which you can actually write a query for, and actually it's very interesting that I'm talking to the database community. I don't know how many of you have seen CodeQL. If not, actually, I would really recommend seeing it. It's very nice, actually. So what CodeQL does is that it takes the parse tree of the program and persists it as a database, right? So that program analysis questions can be written now as database queries. So it's a combination of a relational database and an object database. Now you can actually write, for example, the format, the vulnerability I mentioned, right, can actually be written down as a CodeQL query. Can there be a path from a source to a sink without a sanitizer? You can actually write that as a CodeQL query. So what we do is actually, usually people write CodeQL query for detecting vulnerable code. We write a query for detecting good code, which actually is not vulnerable. And then using these annotations, we actually perturb it and then create vulnerable fixed pairs. And then what we do is actually we feed these things into a program synthesizer. And the synthesizer we developed also is very interesting. I won't get into details of that, but it actually understands heap, it understands many complicated things, and deals with non-local data flow and so on. And then it can learn rules. And then we use these rules to actually post-process the output of Codex. And I just want to give you some stats. Because this CodeQL can be very easily run, we took 200,000 GitHub JavaScript repositories. We considered two classes of vulnerabilities, dynamic call as well as cross-site scripting. Using a bunch of files, we learned some rules, and then we evaluated this on 330 files, and then you can sort of see Static Fixer as our tool. It is able to fix this many vulnerabilities. The other thing we did was that we took the same data set and we tried to fine-tune something called CodeT5, which is actually a neural transformer. And this one, we actually tried to prompt Codex itself with those examples to see whether Codex can actually learn fixing these bugs by itself using the same data set. And because of the intricacy of and the non-local nature of these things, right, the rule-based systems perform much, much better in this. And with cross-site scripting, the gap is actually even more. And this is actually work under submission, and these are my colleagues that I did this work with. So that's actually, and then the other thing I will say is that, so all of these don't touch the model. They actually only think about post-processing, either to filter or to transform the code that is produced by the model. I now have some collaborators, people like Aditya Kannade, who actually have enough skill to actually go and fix the model itself, like, figure out how to get the model to generate the correct code in the first place. And you could sort of think about it as the generating models from that samples from a distribution over programs, conditioned not only by the prompt, but by a specification which actually says that information flow vulnerabilities cannot happen. It's possible to do that. That one is actually more complicated, and we've been working on this for a while. Hopefully, we'll have some ways to do this, and I can report on that at that time, right? But stepping back, what we're really doing here is that we are taking large language models, and then on top of that, we are actually learning rules to improve correctness, remove vulnerabilities, and so on. And in some cases, actually, we can do that. In some cases, because we are incomplete, we actually monitor what users do to get correct programs, and then we learn from user feedback, and we can learn rules from those as well. And I think these things are very, very important. These things are very important. And as these code assistants get more and more widespread, my belief is that these kinds of techniques will also become important. And just like we verify human written code, I think we will have to verify machine written code. We have to change it. And this is indispensable. I mean, I think the quality of these things gets better and better, right? I mean, like even we started this research about 2 years ago. And if I look at the code generators now, the number of errors they make now is actually far less than what they used to. But it doesn't mean it is zero. And the number of errors is moving around. There's different kinds of errors that they're making. But in critical errors like security vulnerabilities, I think are so important that these kinds of techniques, I think, are going to be continue to be very, very useful. So I have two more, and which I'll maybe go through them quickly, 2 more experience reports. The second one is called heterogeneous data extraction. And this is a problem where we take machine to human emails like travel emails and so on, and we want to extract entities from them like departure time, arrival time. Actually, is that a project of the header? It's also the same. Okay. So this is actually probably all of you use it, right? I mean, I was just looking at it just before I got on this podium. I'm actually taking a flight back home this evening, and I don't know whether you can see it. I have a calendar in here, and if you click on it, right, it actually shows that I'm leaving from Bombay to Bangalore, and it tells me everything, and I can actually check it. I can actually click and then I can check it. By the way, this is the code that I'm going to show is actually what runs here in Outlook. So to generate this, and this got generated from the an email that I just got, right? And that's you could say that's a passing problem. But you guys in the database community, you know that this is not a simple passing problem because there are so many formats. The formats keep changing, and even within every format keeps change, and the new formats come in all the time. And this extraction code should continue to work. And the real difficulty with this is that you can probably do some sort of reasonable job, but particularly, right, if you want to get departure time right, you have to be careful. Otherwise, you can send somebody to the airport at the wrong time. That can actually happen. So the way, so more generally, right, we have a term for these kinds of documents called formed documents, and this one is travel, this one is like an invoice, GST, and so on. I was talking to some people in our finance team. They said, no, I get PDFs with all of these things, and I was giving this talk somewhere, and one person came to me and said, I have a lot of forms that my vendors give me. Can I now use your tool to extract, GST and so on? Because currently I have a bunch of people just doing this manually. They look at these PDF files and just do them. So it's a very common problem. But the thing is actually, whatever you have to actually handle all these heterogeneous formats and actually evolving formats, which will continue to change. So the way we built the system is that we use machine learning, where we annotate a bunch of test data. So you think about this as American Airlines, Delta Airlines, Frontier Airlines, and so on, and we build a neural model based on labeled data. But the difficulty comes when you have at test time, you have a new airline or a change format that you have not seen at training time. Then actually what you have is actually you get lower precision. In some cases, actually it works, and in some cases it doesn't work. It turns out, and actually the difficulty is that you don't even know which ones are right and which ones are wrong, right? But suppose you have the conviction that actually a majority of the ones are correct. Then what you could do is that you could now use program synthesis as a regularizer, and you can actually design a programming language which by construction has what is called an all or nothing property, in the sense that it either works for all cases or doesn't work for any case. It's actually possible to actually design such domain-specific languages. And using that, you can actually take these noisy labels and convert them into cases where they are all right. And I'll show you a reference on actually how to do that. And then you can actually feedback this and actually even improve your neural model. And this technique, we published this in PLDI 2019, where you take labeled inputs, where the number of labeled inputs is very, very small, and then we train a model. But the unlabeled inputs is very, very large. Think about labeled inputs as thousands, and unlabeled inputs could be in millions, right? So essentially, there could be millions and millions of emails that people receive, but we have annotated only thousands of them. And then, so when we take these unlabeled inputs and feed it to the ML model, the output is usually noisy. And then we can actually use the synthesizer and get better accuracy, and then we can feedback. And the system, we published in 2019. And since then, we did something very interesting, which is that we now have this system deployed, and then we can learn many things from it from the deployment. And one thing we learned was that, actually, I'm really sorry, actually, you can't read it, but maybe I'll try this, right? So what we find is that because of the programming language we have, the way the programs are generated, it actually counts the number of fields in particular ways, very concretely. And as a result, if there are extra stuff that is introduced, it actually breaks the code. We find that it does that. Like, for example, what happens here is that what this code is saying is that to get the departure time air, take this block air, select the sixth last child, which is 1, 2, 3, 4, 5, 6. That's where the depart is. And then followed by the second child, which is sort of the departure time. That's how it picks it up. And it turns out that if I now add an extra field, then the correct output, is departure time is 8:18. But if I add this extra line, it sort of becomes something else. It can happen. And if I add, like in a hotel or something like that, then it actually also messes it up. So one of the things that we found that's very interesting is that even though these things change, right, the local context of something like a depart doesn't change at all. So this, I have a colleague, Suresh, who described it in the following manner. He said he now lives in London, and he says, if I want to find the McDonald's near Liverpool Street, and I give you any map, each map will be different of London, right? The easiest way to do it is to actually locate the metro station in Liverpool Street. And then from metro station, you can say, go straight and then turn right, and you can always find the McDonald's there in that map. And this map will look very, very different, but for all maps, actually, this idea works, right? So and then he came up with this idea, and his insight was that the metro station for this is actually this depart tag that is present. So you might actually change this format, but actually typically people don't change this tag. And the reason why they do that, because that's what the humans use to identify what the departure time is. So what we now do is that we anchor this program synthesis around these, what we call as landmarks. We call these as landmarks, and we identify the landmarks also automatically. That's what we do. And I can go through sort of more details of how landmarks are identified, but actually the bottom line is that we decompose this extraction problem into a landmark extraction problem and a region. We extract a landmark and a region around the landmark, and then we do the extraction only within the small local region. And this enables us to be robust when the formats change outside of the region, right? It actually continues to work well. And we have a paper last year in PLDI where the accuracies improve. Like in many cases, actually, we get 100% accuracy. This new algorithm is called LSN, and then other cases actually we get really, really good accuracy. And one of the things we did here was that we actually went from just HTML. We also now handle images. We can actually take PDF images. We do OCR, And then from the OCR, we can actually do extraction from them. We are able to do that as well, right? So stepping back, right? In all of these, what we're doing is actually we are starting with a machine learning model. Then we are using a synthesizer. And then the extraction programs we get are interpretable, unlike the machine learning model. And I know the team that worked with us on this airline extraction. They would not ship anything unless they can actually code review it and at least departure time, airport, and so on. If they don't review the code, they won't ship it. This is just how it is, right? Because these things, unlike an advertisement where something can go wrong and you might actually get a wrong advertisement, the dissatisfaction penalty for that is actually quite high. So in some sense, right? In that sense, actually, it improves interpretability and also it improves performance. These models are very large and these programs are extremely small and they can actually execute it without much footprint. But we go back only if the labels that are generated are not of good quality. Then we sort of go back, resynthesize these programs and run them. And this kind of methodology actually works very well, right? I will just go do one more thing. Do I have time to do one more case study? Yeah. The third one is actually a collaboration with Sunita and her students, where we are combining machine learning models and rules for regulatory compliance. So let me just describe what this problem is. Right. So Bing or any other search engine, when you search something, it actually shows many advertisements. It turns out that these kinds of systems use both machine learning models and override rules to satisfy regulatory obligations, right? Every country has legal obligations on what ads you can show and what ads you cannot show. So India, for example, you cannot show alcohol, you cannot show adult ads, you cannot show tobacco, firearm, you can't show any of those ads in India. Alcohol, I think, is allowed in some other geographies and so on, right? So how does actually a search engine ensure this? What they do is that they have many pipelines, but a lot of control actually happens during ingestion itself. When they submit the ads, right, there is a classifier that runs on the ad to categorize the ad, saying what category does this ad belong to. And if it belongs to something that the regulation in the country does not allow, then they don't accept that advertisement. That's how it works. But as you can imagine, right, the runtime distribution is different from the training distribution. As a result, you can get both false positives as well as false negatives. You can get ads that are not supposed to be shown that can get shown because the classifier can be too permissive, it might let it through. You can also get ads that are harmless and can be shown, but are somehow blocked. And as a result, the ads platform loses revenue because it actually doesn't show. Both those things can happen. And what I found very interesting is that the way a practical ad system deals with it is by using override rules. The way it works is actually that somebody complains saying, my ad should be shown. Why are you blocking it? That's a typical complaint that actually these people get. And when they get it, what they do is actually they look at that ad and say, oh, this ad should be submitted, should be accepted. And then they write an override rule saying, actually, if your ad has these kinds of keywords, let it in anyway. And they write it as an override. And over time, what happens is that millions of such rules get accumulated because every time there is a complaint, it is actually very hard to go retrain a machine learning model because it actually takes weeks to actually retrain a model and so on. So and customers don't have that much patience to wait for the machine learning model to get updated and so on. So people just write these override rules. And so one of the things that we are working on is how should you combine these machine learning models and these override rules? The current state of the art, at least in Bing, is to think about the rules as very hard overrides. They are just first the override rules are applied. And only if the override rules don't apply to an ad, then it is actually taken through a machine learning model. But the difficulty is that it's very hard to write good override rules. So for example, right, this here, what's happening is that the ML model admits psychoactive plants for whatever reason, and then the immediate reaction is add psychoactive as a filtering rule, saying if your ad contains psychoactive, don't show it. That's the override rule. Somebody has done the same thing with tobacco, but then there's this ad which says tobaccomotorwear.com. That also gets blocked. Now they write something saying, maybe if it also has tobacco and jeans, maybe let it in. right? So you can sort of imagine, how difficult it is to actually do this, right? So the work we did is to take the ML classifier and take a set of override rules and come up with a soft composition operator that somehow combines the machine learning rule and machine learning model and this rule, which you could sort of think about it as a conjunction of unigrams and bigrams, with sort of the following interesting properties, right? So what we do is that for every rule, usually there's an exemplar, because that was the instance which actually triggered, which was classified incorrectly, which resulted in the rule being written. And so we actually learned two parameters. One, a radius, which is the distance from the exemplar, where we think that the rule we can have high confidence in, because the points that are near the exemplar, we have higher confidence. The points that are further away, we don't have. And actually, we can learn that by using the training data itself, because we have training data in which the labels are already present. And we use the ground truth gold labels to actually learn these two parameters, alpha, and the other one converts the distance to distribution of class labels. And using this alpha and beta, in some sense, we are using the data to tell us when to trust the rule and when to not trust the rule. That's what we actually are doing. And we also use, the one thing that I didn't say is that it is not just about restricting the scope of the rule, it's actually also about allowing synonyms and so on, right? So for example, maybe we wrote only, the marijuana, and then psychoactive maybe has an embedding that is actually similar to, so by using embeddings, you can actually find similar terms and so on. So we try and do both. And so as a result, right, so there are examples where the rule only mentions smoke, but psychoactive plants is actually also covered by smoke because the embeddings are similar. This one is, is about genes. Even though there is tobacco, right, the alpha and beta are learned in such a way that this is far away, maybe, from that rule. So that's actually how it works. And we came up with a compliance error metric, and we have compared the compliance error metric between this hard compose and the soft compose. And the soft compose performs better, and this is also under submission. So I'll now conclude by stating that in all of these three experiences, be it Jigsaw and static fixer, our work on entity extraction or soft compose, all of these, we in some sense, right, these systems inherently have both a machine learning model and rule inside them, and the rules are providing interpretability in certain cases, robustness, improving security, and improving performance, because they have such small footprint, and you can actually run them with much higher efficiency than what it takes to run an ML model. And I think actually this will continue. Even as ML models get better and get more pervasively deployed, I think we will see this. I wanted to conclude also by pointing out, I know there's lots of PhD students here. I want to point out opportunities for actually further research that you can think about. So I'll point out three. If I really think that Copilot is only one of the applications for large language models. There's going to be many more, even inside software engineering, because in software engineering, people talk about an inner loop and an outer loop. How many of you heard the term before, inner loop and outer loop? Only a few. So inner loop is actually what happens inside with one programmer. So I'm sitting before a console, I code, I compile, I check in. So this is my developers, that's my inner loop. A large team has hundreds of people, each of them having an inner loop, right? And then the team itself moves together. That's actually called an outer loop. The outer loop involves integration, testing, and so on, and code review, because when I check in code, actually somebody else has to review the code. And only then it's actually approved to check in, right? And then there's a person who does security review. People have to do security review before a code can be merged into a main branch. So all of those things are actually called outer loop, right? And typically what happens, if you work in a large team, actually before doing my PhD, I used to be a programmer in a big software company. And I know that the amount of time I wait for things to happen is actually more than the amount of time it takes me to code, because that actually involves other people. And I don't know, a lot of people are here from the industry as well. That's true, right? The outer loop is actually much more demanding in time-wise because it involves people coordination, right? I think actually of course, actually you can suggest code, but if you can suggest code reviews, if you can suggest security reviews, the amount of impact that will have on the speed in which large software engineering teams develop is going to be an order of magnitude more. So outer loops actually are all called workflows because workflows happen when multiple people have to do things, and you can actually write down a workflow like a flow chart. And typically, these workflows have manual steps and automated steps. For example, testing is a step which can be automated. You have to run a test, you can have a machine run it for you. But writing a code review is something that a human has to do. I really believe that every step that in a workflow, in the outer loop of the software engineering system, where a programmer or some human being needs to be involved, can be now improved by using an assistant, much like Copilot. And I think this will happen. This will definitely happen, right? The second thing that I find very interesting is that these large language models are leading to a new class of applications, right? And I've been writing code with these things. It's very, very different to program these things. There's something called prompt engineering, thinking about multimodal inputs. And I think just like we have Visual Studio and development environments for today's applications, I think an entirely new development methodology and tools for these LLM-based applications will also happen. There's no doubt about it in my mind that it will happen. The third thing I'll mention is, I remember I was talking with people like Chitra, Viraj, and there's a lot of question about how these LLMs are going to influence education, and I want to write two views on that. And there's an opportunity, I guess, in education research in thinking about how these things will likely change. And my own view is that CS programming courses will definitely change, but perhaps actually not the introductory courses. And the analogy I would give is, we do, even after calculators, we do teach math to kids. We just take away the calculators when they come to the exam, and they learn to add and subtract, at least so far. And in higher grades, we just give them the calculators, right? Because we know that we have learned them. So to me, it seems like that could work. Then that in introductory programming, of course, you can't prevent them doing whatever they want to do in their homework, but at least in the exam, you can lock them up in the room and not give them that and make sure that they learn it. But I think senior level programming courses, I think there is a real opportunity. There is a real opportunity in allowing senior level students to actually use these tools and actually perhaps give them more complicated projects than actually what you're able to give them. Raise the bar on them and make it part of the curriculum to sort of construct course material on how to actually use these LLM outputs, making sure actually that you inspect the kind of vulnerabilities that I showed. Those things do happen. Reading, reviewing, collating, integrating code. Make sure that you have to integrate. You have to actually your assignment should be complicated enough that it cannot be just generated by one invocation of an LLM. Make sure that they have to do it multiple times, and it is their job to actually take all of those suggestions that the LLM gives, put them together, pass a big test case, and so on. So then actually, this is actually how they would use it in the industry when they graduate, right? So I think I think there's a huge opportunity. I think there's also a real opportunity with these LLMs for non-CS students to get into programming. I think CS is kind of intimidating to non-CS people. I've actually talked to many of them who are scared by the syntax, particularly actually if you talk to biologists and economists and so on, they are scared by the semicolons that we have and the parentheses, the balance. They need to balance them, and then some cases the indentation. If you just miss the indentation, right, the whole thing bombs. It just scares the hell out of them, right? I think it is a democratizing opportunity for non-CS people to do programming, and I think we need to educate the students on testing and validation. Perhaps actually not as much on programming. So with that, I'll stop, and I'm happy to take questions here.
So thank you, Sriram, for a wonderful talk. I think there's a lot of food for thought in this. A lot of PhDs can come out of this. So it is wonderful. We have time for several questions. I'll give Sunita the first chance. for writing a paper.
Hopefully they'll accept it with the
We
caveat.
hope so. Yeah. Yes. So, just wonderful talk. Actually, your talk led me to think about whether we should redesign what we call as a computer programming language now to be a language in terms of natural language instructions, which codex or whatever can understand. So then we just sort of, Python was supposed to be easier to write than C. Now, similarly, maybe now we should think of instructions which are like subroutines, natural language subroutines, which can be then automatically converted into C, now then will be later converted to assembly. So we are just moving one level ahead. And so basically, can we identify what the natural language instructions are, which guaranteed correctly will be converted into Python snippets or C++ snippets? And then what we teach is basically how to create what you call the outer circle, the outer loop of programming.
That's very interesting, right? I actually,
So it's just time to invent a new language.
probably, but I also wonder, there is a paper of Percy Liang that I was reading called Voxel World, and Voxel World is very interesting. I think it's and the reason why I think it's relevant is that one of the things that Percy does, I think, in Voxel World is that over time he actually doesn't fix the phrases in his programming language. He lets the users program with whatever nouns and verbs they are comfortable with. And over time, actually, he learns what the meanings of those words are. To me, actually, what you say, Smrita, is very interesting, but I think there's an extra opportunity with LLMs that we don't have to even fix this language, right? Generate whatever, and then
All the biologists and all, we just talk to, they basically write a sequence of natural language.
in whatever they want to do. And then I think there will be a feedback loop with RLHF or whatever, right? Where actually this thing can actually, the programming language might just look, the biologists can chart the course of their own programming. I think that's something, it's possible to do a change at a meta level, even with that, where the users, the community can actually perhaps actually influence how a programming language goes.
So, but for that, verification people have to certify which are natural language expressions for which we can reliably generate. Correct.
Yes. So one other thing that I think that's interesting there, Sunita, what I feel is that I think what we need to do is, for that to happen, right? I think we also have to have testing, test cases. We have to have some, for verification people to do something, right? We need to have some other specification of intent that is perhaps not complete, but more precise than natural language, right? Similar to what we did with pandas, right? At least some test cases. I think in every domain, I think it is important to also ground that with more precise specification of intent, and then the verification people can actually do that happen. Yeah.
All the PhD students here. Yeah, to all the PhD students here, you got an example of how to write a paper, a live interactive session.
You can write a biology LLM paper for you.
Sir, great talk. Thank you for this session. So, in your first work, you had said that you use some rules, like suppose a variable change or changing in the arguments, and a third is and also you learn what changes the user makes to correct the program, and you accumulate those rules and you apply those rules to the further output by the LLMs. So, do you think this process can be automated again? And do you think that, or you are already working on that, this program correction or optimizing a program? So, maybe a code is output by the LLM that is not fully vectorized or stuff like that. Do you think there can be automated methods to do that?
Yeah, so actually, it's a very good question. So if you look at actually our jigsaw work, right, I presented two things. The first thing I presented is when sort of the transformations, we designed them by hand, right? What we did was actually swapping the variables or mutating these, and those transformations, we designed them by hand. That's kind of limiting because, in some sense, that's not sort of dynamic enough of data-driven learning. If you look at our second piece of work, right, where I sort of showed you how to fix these vulnerabilities, that we did in an entirely data-driven manner. So for example, there, I don't actually ahead of time as a tool designer, I don't say how to write those rules, right? I just actually look at all the vulnerabilities that are present, and I generate correct code pairs for them. And from there, actually, I learn the rules, right? And this is our evolution in thinking. I think the rules don't have to be fixed ahead of time. The rules can be learned from users and usage, much like machine learning works, right? And I think the rules, all that a designer has to do is to come up with a rule schema or a DSL or something like that. And the rules can be learned from data as well. And increasingly, the latter makes more sense to me.
So let me push, I'm here.
Yeah, hi.
So let me push Sunita's question a little bit more. And I actually read the article about the end of programming on the flight over. So
Yeah.
what should we be teaching our students? Should we be teaching them the data structures and the algorithms and the complexity, all that stuff? Or is it how to interpret what these models are doing, the resiliency aspects? I'm just curious, are we facing a whole new way of education for undergraduate computer scientists?
Yeah, I feel actually that in 10 years, if you actually integrate over a period of time, I sort of see that there will probably be a huge disruption. And I think, I do believe actually many of the things that the End of Programming article says, which is that I think, Matt Welch makes the argument that just like the number of people who program in assembly right now is very, very small, the number of people who need to learn data structures and so on will become smaller, which is probably, I agree with him, that's probably will happen. But I also think that this doesn't mean actually we don't teach people assembly language. Actually, I think even now, actually, people go through a microprocessor course. And if you want to have a core CS degree, they go through an architecture course where they learn. But I think what happens is that now there are CS programs, maybe you call them AI programs or data science programs or so, which have gotten rid of those courses entirely. So my sense is that there will probably be a data structures course, but 5 years from now, less people will take it. Because there will be computer science programs, which, yeah, that my guess is that's probably what's going to happen. My sense is actually that there will be, just like actually people still program in assembly language, but a much smaller fraction of the computer scientists program in assembly language. So my sense is that there will be a data structures course, but a much smaller fraction of graduating CS students will have to actually take it. And for a large majority of students, we will have to design curriculums without actually teaching them, pointed data structures and so on. That's actually my sense of actually where the world is going, right? And I also think actually that it's a huge opportunity for non-CS people to get into programming. And I think when we went from assembly to higher level languages, I think a lot of people, the number of programmers increased. I think that we're going to see a huge increase in the number of programmers. So I think computer scientists, I think we'll have a job, but we'll have a different kind of job, is what I feel. Yeah.
Okay. Beautiful talk, first of all. So I come from, pure NLP and language perspective. So, so as we learned in grammar, there are 4 kinds of, sentential constructions. So declarative, interrogative, imperative, and exclamatory. So what programs do is essentially concentrate on imperative sentences. Okay, sort these numbers for me, the instructional order. So now, if we look at the history of evolution of programming languages, very persistently we moved from lower level tasks to higher level descriptions, and the need was abstraction and concentrating on what to solve rather than how to solve. So now this had to happen actually. What we are seeing now.
Right. So SQL is an example. SQL is an
yeah,
example of that. Yeah.
Right. And language had to be used for programming machines. I mean, this was inevitable. So now the point I'm trying to make is that a huge amount of language constructions are what are called speech acts. Speech acts.
Okay.
So tense, for example, is past tense, future tense, present tense is a very important language construction. Then wish, intent you refer to. Then subjunctive mood. If I was the president of India, then I would do something. So while language programs human mind, which is capable of dealing with such phenomena, I don't think this is in the purview of what we are discussing now. So just wanted to know your thoughts on this.
Very, very fascinating, I think, right? In fact, actually, what I feel is that, but I don't know, what I'm very intrigued by is the following. But we probably use all that information to decide what to do, right? So those are not probably part of explicit instructions that we give ourselves to do, right? But I wish I had actually studied machine learning when I was younger. That's something I always think about. I took programming languages. I wish I had studied machine learning when I was in grad school. I would have much more intentions, much more intuitions actually about them. Something I feel, right? But I think we use those to actually influence our actions in some way. So what I wonder is that for these LLMs, I think what they eventually do will be actions, but those actions might be influenced by these more subtle kind of language that they probably will gather over time. Is what I think. Yeah. Okay. Thank you. Yeah.
Thanks for a great talk. These LLMs, they are generating code in various high-level languages. But the second use case that is specifying where user is giving input in natural language and the machine is going to execute it in binary machine code. Can we skip this intermediate representation of high-level language? Will it make any sense? Will there be any advantage?
Yeah, so I think this is related to the question that Sunita asked, right? Which is, do you even need a machine-readable programming language, or can we just give semantics just based on natural language itself? I think it will happen. It will happen in many cases where you will have a set of nouns, verbs that a community is comfortable using, and there will be some semantics on what it means to execute instructions in that language. I mean, I can imagine actually 5 years from now, you have a command prompt. I don't think you will write, CP -R here to there. I might write, take all the photographs where me and Sudarshan are both present and email them to me. I should be, I should be able to write that. And it's probably possible to do that, right? Because, you probably could image processing to figure that out, right? And I should be able to email it to me. It should be possible, I would think. Yeah.
So there is an online question. I will put it on a screen for you. Okay. What we have observed is that these LLM models generated codes are non-performant. What is your thought on getting performant code for a given hardware architecture using these large models?
So I'll give you two answers to that, right? And it's very destructive for my own research, right? One thing you can do is actually I can say, you take that and then you do post-processing and so on and make it more performant. I mean, that's one way, right? But I believe I'm losing because these things are getting so much better that every generation of them is getting so much better. There's only two answers I'll give to you, right? One thing you can do is to just wait. They will get better because as more users use these things, they will get better. But if you are in a hurry, right, you could do what I'm doing, which is you could write post-processing things, other kinds of things on top of the LLM and use the LLM as an aid and program on top of them. But I'm stunned by how good they're getting. So you could just wait, and they'll generate performant code. Yeah.
Thank you. We are running out of time, but I will just allow myself one last question as session chair, and then we'll close the session. So there's a lot of work on low-code, no-code application development.
Yes.
So has this sort of technology had an impact in that area? Because there's tremendous demand for these things.
Yeah, exactly, right? So in Microsoft, actually, we have, along the lines of what you're saying, Sudarshan, right? There is Power BI, ActionScript. There's a bunch of things, right? And all of those languages have natural language interface to them. And they're all powered by LLMs. So all of the low-code, no-code solutions that at least Microsoft now provides have an LLM-based interface where you can actually just talk to it in natural language. And I wouldn't be surprised if instead of Excel macros, you'll be able to write natural language. And I think every company will do it. I wouldn't be surprised if every software that you use which has menus, where I need to click a bunch of menus and do something, there'll be also like a box in which I can actually type what I want to do, and the thing will probably just do it. There's no doubt that'll happen. Yeah.
Fantastic. Thank you for this wonderful view into the future. So it was an excellent session. We, of course, overran the time. So I think the next session will start at 3:40, 10 minutes late.
Thank you.